Good afternoon. We're going to get started with our webinar in just a few moments. Okay, it is 2 o'clock, so I am going to start off the webinar. Good afternoon, and thank you for joining us on our call today. My name is Nicole Van Wert-Quincy from Transcat, and I'll be your moderator this afternoon. Our webinar topic is tips and techniques for high-pressure calibration. This topic is being presented by Tim Francis from Fluke Calibration. Tim is the marketing manager for pressure and flow at Fluke Calibration. He began his career in pressure metrology in 2002 at Ruska, where he was an applications engineer. He joined Fluke Calibration in 2010 following the Ruska acquisition. He holds a bachelor's degree in computer science from the University of Texas at Austin and an MBA from Arizona State University. Tim works in the Fluke Calibration facility in Phoenix, Arizona. We expect the presentation today to last roughly 30 to 40 minutes, and then we'll answer any questions that have been submitted during the presentation. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. And at this time, I'm going to turn the presentation over to Tim.
Thank you, Nicole. Hello, everyone. Thank you for joining us. As Nicole mentioned, our topic today is on high pressure calibration. We'll be looking at different tips and techniques for doing that. Our agenda, first we'll cover some just basic vocabulary and the physics of pressure, making sure that we're all starting with a good foundation. Then we'll look at some of the special considerations when working with high pressure and what makes high pressure unique. And then we'll end the discussion with a brief look at how to determine what equipment to use for high pressure calibration. So let's start first with a definition of pressure. Now pressure is, as they say, a derived measuring. And what that means is there isn't a vessel sitting in a vault in France that's exactly 1 psi or 1 kPa. It's not like the 1 kilogram. There's no definition for it in that frame of reference, but instead it uses the base quantities, things like mass, length, and time, as part of its definition. And specifically, pressure is defined as force divided by area. And we see that in the most common pressure unit here in the US, pounds per square inch, where pounds is a unit of force, and then the square inches being area. Now, pressure describes the condition of something else, and specifically the condition of a fluid. So we're looking at hydrostatic pressure measurement. That is the pressure of a fluid. So as I say, it's a state variable where it's a quantity that describes the condition of that fluid. That is that the fluid is at 100 psi or 1,000 psi. It's important to note here that when we say fluid, the scientific definition is that a fluid is either a gas or a liquid, and not perhaps the common definition we may think of in our heads of a fluid being a liquid. But instead here, it's to capture both gases and liquids as being fluids. Our pressure can define either a gas or a liquid. Now, most of the pressure measuring devices that we deal with measure over a given range. So like a dial gauge may read from 0 to 100 psi or 0 to 1,000 psi. And so when we talk about pressure calibration, we're calibrating it over a range of pressures. And as stated before, measurements are made in some type of fluid, either a gas or hydraulic fluid. So it is either a gas or a liquid. But what is high pressure? Well, there's no strict definition. It is very much a relative term. It depends very much on your experience, the application, specific governing rules. We have one part of our business where they focus on very low draft range measurements, things that are inches of water, the difference in pressure between one room and another. And to them, something like 30 psi is high pressure. But for most people in a normal process type application, 30 psi would be low pressure. So it is very much a relative term. It's very dependent upon your own experience. For the scope of this discussion, we're going to consider pressures that are about 3,000 psi and above as being high pressure. And why do we choose there? Well, most gas cylinders here in the United States is about 2,200 psi. Some will go up to about 6,000 psi, but 3,000 is a good round breakoff point there. And when you start looking at different instrumentation that's available, 3,000 psi is a common break point there. So it makes sense to consider that as our defining line here. For many of you, you may think of, well, it's not really high pressure until it gets above 10,000 psi or 20,000 psi. We'll be discussing those ranges as well, but we'll consider things as low as 3,000 psi in our discussion today on high pressure. So let's talk about some of the terminology and make sure we're all on the same page. When you see pressure values, they're sometimes followed by the words gauge or absolute. And sometimes it's abbreviated into the pressure unit, and you'll see something like PSIG or PSIA. What does that mean, and why is it important? Well, all measurements are relative. So as the example here is, you don't say that I live 5 miles. That doesn't tell the full story. You say, I live 5 miles from here, or I live 5 miles from my work. So that measurement, that distance measurement, has a starting point. And pressure is no different. You have to have a starting point to your measurement. To simply say the pressure is 5 psi, that's not quite enough for somebody to understand the whole story. The more proper saying, or the way to show all of the information, is that the pressure is 5 psi above atmosphere, for example. The terms gauge, absolute, and differential are simply shorthand for this, for providing that full bit of information. So let's look first at gauge mode. Gauge mode means that it's referenced to atmospheric pressure. So your starting point is atmosphere, is the air around you. So zero gauge means that your test pressure is the same as atmosphere. This is perhaps the most common reference mode. And it can be both positive and negative. So a negative gauge pressure means that you're below atmosphere. It's a partial vacuum. And a positive gauge pressure means that you're above atmospheric pressure. And this is often, this is the most common reference mode, and it's also the easiest to measure. Part of that is that you have a well-defined 0 point. If your test pressure is vented and open up to atmosphere, then by definition, you know that it's 0 gauge pressure. And so it's easy to zero the instrument and make sure everything is correct. Some examples here, your basic tire pressure measurement, and also many process measurements use a gauge mode measurement. What's important here is to consider is that for high pressure, many of the measurements that need to be made are gauge mode measurements, but a lot of the pressure sensors that are available, pressure devices that are available, are actually absolute mode. So we need to make sure that we consider that in our calibration and correct for that. So what is absolute mode? Here, it's referenced to a perfect vacuum. So that starting point, instead of being the atmosphere around you, the starting point is a absolute 0 of a perfect vacuum. So that means it can only be positive numbers. A 0 means perfect vacuum means there's absolutely no molecules inside of your system. So if you had a negative absolute value, that would mean that there's a negative number of molecules in the vessel, and that's just simply not possible. So it's always a positive number, and it is a more difficult measurement, because here, how do you re-zero the reference? If it's opened up to atmosphere, it should not be reading 0. It should be reading the atmosphere barometric pressure. So to re-zero it there, you have to you have to compare it against a sufficiently accurate standard that's reading the barometric pressure. You say, okay, well, I'll just pull a vacuum on it, and I can re-zero it that way because vacuum equals 0. Well, you have to. There's no such thing really as a perfect vacuum. It's extremely difficult, if not impossible, to reach the point where there's absolutely no molecules in your system. And even if you could get there, you'd have no way of knowing that you're actually there. So once again, you would have to compare it against some sort of vacuum standard to get the most accurate reading. So that makes it a bit more difficult, but not impossible. And for most applications, the zero drift perhaps could just be considered in the overall uncertainty, in the overall measurement, and is insignificant for the application. Some examples of absolute mode pressure measurements, the barometric pressure. So as I said, when you're open to atmosphere, it's not going to read 0, it's going to read that barometric pressure. Approximately 14.7 psi at sea level. At higher altitudes, the barometric pressure is lower, and that phenomenon is what's used for like the altimeter in an airplane, is simply doing an absolute mode measurement of the atmosphere around the airplane and converting that to an altitude based upon that barometric pressure. Other places where absolute mode is used is, for example, in the oil and gas industry on a downhole tool, because it's measuring the pressure at the bottom of the hole. There's no way to compare it to the pressure at the top of the hole, so it's an absolute mode measurement. The other mode that we'll talk about here is a differential mode. So that's where the pressure is referenced to another pressure. That other pressure is something referred to as the line pressure or the static pressure. And here 0 means that there's no difference in the two pressures. You can think of gauge mode as being a special case of differential mode, where the line pressure is atmosphere. So oftentimes you'll see something referred to as a differential mode unit, but it's only operating at where the line pressure is atmosphere. Differential mode can also mean where the line pressure is elevated to be something different from atmospheric pressure. A differential pressure can be both positive or negative, because it can be either above or below the line pressure. And this is a very difficult measurement to make. There's few calibrators that actually support a high line pressure measurement, a high line being one where the line pressure is elevated to some value much greater than atmospheric pressure. Some examples where this is used, an elevated line pressure example would be the flow measurements in a pipeline. So the pipeline will be at some line pressure, some elevated line, perhaps a few hundred psi or a couple thousand psi. And then the flow measurement is done by having some sort of orifice that creates a differential pressure as the media flows through the pipeline. And you measure that differential pressure to determine the flow. Another example is the draft range measurements, the difference in pressure between two rooms. So one room would act as your line pressure, and the other one would be the differential, and you would be looking at the difference between those two rooms. There, your line pressure is atmospheric pressure, very close to it. So it is a differential measurement, but it's at a low line pressure. As I said, it's important to understand the difference between these different reference modes when looking at high pressure, because you may be trying to make a gauge mode measurement or need to make a gauge mode measurement, but the only pressure sensors that are available to you are absolute mode. And if you just treat them as exactly the same, you'll have an offset in your data of 14.7 psi approximately. And that could cause some large errors depending upon your application. Another thing to consider that's very important is what we call head pressure, or reference head height. The weight of a column of fluid will generate a pressure. If you've ever been scuba diving, you've seen this phenomenon, but you can just think about a swimming pool. The pressure, the water pressure at the bottom of the swimming pool, as it's pushing on your eardrums, is greater than the water pressure at the top of the swimming pool. And basically, it's just the weight of the water pushing down on the water below it. It's calculated as being the height times the density of the fluid times the acceleration of gravity. If the reference device and the device under test are at different vertical positions, even if they're connected to the same system with no leaks or anything, but if they're just at different heights, the pressure at each of them will be different. This can cause a problem when we're doing our calibration, because if for example, especially like say you're at a process plant and you're calibrating out in the field, and your pressure sensor is way up high, close to the ceiling, and so you connect up to it, but you're down on the ground and you've got a long tube in between, there's going to be a difference in pressure readings between those 2 points. With liquid, the density is constant with pressure. That is, that liquids we generally think of as not compressing, not being compressible. So the density is constant as the pressure changes. And so our equation, if the height stays the same and the density stays the same and the acceleration of gravity stays the same, then that difference in pressure, that head pressure, will be constant even as we increase the pressure in the system. So it's a constant offset at all pressures. What that generally means is that at low pressures, it can be quite large and cause an issue for us. But as we get up to higher pressures, it's still that same constant value. So say that you calculate it out and it equals 1 psi. Well, when you're measuring 30 psi, plus or minus 1 psi is pretty large. But when you're measuring 10,000 psi or 20,000 psi, 1 psi could be insignificant. Gas behaves a little bit different. With gas, the density increases with pressure. As the gas compresses, it gets more dense. So the error is a function of the pressure. So the height stays constant, the acceleration of gravity stays constant, but the density doesn't. And that causes the pressure difference to change with the pressure in the system. But gas is less dense than liquid. So that results in a smaller head height error. At the same pressure, it'll be a smaller error. It's also important to note that some calibrators will make the correction for you. So you'll just have to tell it what height difference your device under test is, if it's 3 feet above or below the calibrator, and what gas or liquid you're using in your system, and it can calculate the difference and make that correction for you. What we'll find is that the reference head height is an important thing to consider when choosing what media to use for our calibration. And as I said, it can cause an error that, if we don't account for, could be significant in our calibration. The other thing to consider with pressure is the stability of the pressure. In order to make the measurement, the pressure needs to be stable enough for us to know what that pressure is. Unfortunately, pressure is inherently unstable. And why is, well, it's affected by other things. And we see that when we look at the equation here, which is the ideal gas law. And in this equation, the P equals pressure, V equals volume, N is the number of molecules in the system, R is the ideal gas constant, so it stays the same, and T is temperature. What this tells us is that pressure is impacted by 3 things: the number of fluid molecules, that is N, the volume of the system, and the temperature of the fluid. Let's talk a little bit more about the number of molecules and how that affects the stability of the system and how we can take advantage of it. If the number of molecules in the system changes, then the pressure will be unstable. Well, why do the number of molecules change? If we have a leak, that's basically the number of molecules changing. That is, the molecules are leaking out of the system. And that leads to instability in pressure. It can also possibly result in measurement errors, because it'll create a flow, and flows across an orifice can create a difference in pressure. So we want to keep leaks to a minimum in our system. Now, there's always going to be a leak. Even in the most, even when we take the greatest care possible, chances are there's still going to be a leak. Some of these molecules are really small and they'll just find their way out. But if we can take care to make sure that the leaks are at a minimum, then we can improve our overall process and we can get to a stable pressure much quicker. It's also important to note that this relationship between the number of molecules and pressure is a tool that we use when we're generating pressure, especially in a gas system. We can push more molecules into the system to increase the pressure, or we can exhaust molecules out of the system to decrease the pressure. Here we show an example of a device that does that, the P5510. It uses the hand pump here to basically pull in air from the outside and through a check valve push that air into the actual test system. So what are we doing? We're pushing more molecules into the system, and by doing so, we're increasing the pressure in the system. And there's also a vent valve that labeled there as exhaust, and that's how we would decrease the pressure, is we can exhaust the molecules out of the system. This works great, especially for pneumatic systems. For hydraulic, we may use it as kind of the starting point, but we find that it gets a bit more difficult, and we generate the pressure a little too quickly, and it's not the easiest approach. So instead, we use other approaches to generate pressure in a hydraulic system. And that's what we see here with the relationship between pressure and volume. Here it's an inverse relationship. As we increase increase the volume, it decreases the pressure, and vice versa. If we decrease the volume, pressure increases. As the pressure increases in a system, especially as we get to these high pressures, the inside of the tubing and the walls will, the pressure will be pushing against those and it'll push them out. So even though this is stainless steel and it's very thick and we think, okay, this shouldn't move, with enough pressure, everything moves. And so as you increase the pressure in the system, it will cause the walls to be pushed out and it'll increase the volume in the system. And if you increase the volume, you end up decreasing the pressure. So that causes the pressure to decrease, and that may look like a leak when you get up to pressure. As everything stabilizes, that leak will go away, but that's an important thing to consider with high pressure systems. Now, once again, we use this relationship between pressure and volume to generate hydraulic pressures. So like an example is the device we show here is the P5514. Very simple. It has that screw press that as you turn the capstan, as you turn it clockwise, the screw goes in, and that decreases the volume in the system, and that causes the pressure to go up. Can we use a volume change like this to increase or decrease the pressure in a pneumatic system? Well, kind of. Here we can, with that screw press, because the liquid is not compressible, the pressure changes dramatically. So we can use that screw press to generate, in this example, 10,000 psi. If our system is full of air, it's full of gas, that gas compresses. So as you change the volume of the system, the pressure is affected, but it's affected in a much lower amount. So instead, we would use a variable volume or a screw press like this, not to make dramatic changes in pressure, but to fine tune the pressure and get it exactly to the set point that we want to go to. And of course, the last variable that affects our pressure is temperature. In an enclosed system, temperature has perhaps the biggest impact on pressure stability. As the pressure is increased, the temperature of the fluid also increases. So there's whereas volume, it's an inverse relationship, here it's a much more direct relationship. When the pressure set point is reached, the temperature will start to decrease because it's going to want to return to ambient temperature. It's going to want to stabilize with the environment around it. As the temperature decreases, this is going to cause the pressure to decrease with it. And that's going to give the appearance of a leak. This is an important thing to consider because, as I say, it's going to look like a leak. Your pressure is dropping, and if you're not careful, you're going to spend a lot of time looking for a leak that doesn't necessarily exist. So what you want to look for here, if it is temperature caused, is that it will leak, but the pressure drop will eventually stabilize out. So if you were graphing your change in pressure with time, if there's an actual leak, it'll be a straight line diagonally down and to the right that will stay at the same rate. If the change in pressure is caused by temperature, instead of a straight line, it'll have more of a curve to it because it will slowly start stabilizing out and will not be leaking as dramatically. So what about high pressure? What are some things that we need to consider? Well, there's three main topics to look at here. First is perhaps the most important is safety. Then we want to talk about contamination. And finally, pressure stability. We'll look at some of the information we're just looking at with what causes instability and see how to resolve that with high pressures. There are inherent dangers with high pressure, but the risks can be mitigated. And why are there dangers? Well, as you increase the pressure, there's more energy in the system. With more energy, you have more potential for issues. Some things to consider is first, make sure you use personal protective equipment. Most common is safety glasses. For very high pressure systems, you may have a situation where you'll need some sort of barrier like a cabinet or so forth, safety cabinet between you and the pressurized equipment. But for most applications, the use of safety glasses or similar PPE is sufficient. What's also important is to make sure that you ensure all pressure lines and fittings and other components, so valves and so forth, are properly rated for the application, are in proper working order. If there's an issue in a pressure system, this is probably the most common culprit, is someone quickly grabbed whatever pressure line was available and said, oh, this will be fine, not realizing that perhaps it's not rated to the higher pressures, or that perhaps it's been used frequently and is quite old and needs to be replaced, and that pressure line ends up bursting and causing an issue. So it's very important to ensure that all the pressure lines and fittings are properly rated. They'll be rated from the manufacturer. Many times you might see two pressure ratings given, a maximum working pressure and also a burst pressure. You should always design into your systems using the maximum working pressure, not that burst pressure. The burst pressure is more of a, maybe that's what they tested to, or okay, you can take it there once, but you shouldn't be doing it repeatedly. Whereas the maximum working pressure is the pressure that you can take it to repeatedly and be confident that it will work properly. Another thing to consider is to minimize the volume of the test system where possible. A larger volume, especially with a gas system, means that there's going to be more stored energy and thus more potential for issue. And then for the highest pressures, consider using a liquid media. Gas compresses. As it compresses, there's more stored energy, so there's more of a challenge there. Whereas with liquid medias, because it doesn't compress, at high pressures, even if the fitting lets go, there might be initially a dramatic release of pressure, but it will dissipate very quickly and it won't be as dramatic as with the gas media. So at what pressures should you be using a liquid media? Well, anything over 15,000 psi, you almost have to use liquid. There's very few tools, equipment available for using gas at those higher pressures, and so it'd only be used when you really, really have to. Anything below 3,000 psi, you almost always want to use gas for the contamination issues that we'll talk about in a minute, and also for head height concerns. At the lower pressures, the gas makes has a lower head height error. For the areas in between, there's equipment available to use both, but for many applications above 3,000 psi, you'll probably go with a liquid media, unless you're using like benchtop systems where gas is available. Why would you use gas? Well, that goes into the next discussion on contamination. There are drawbacks to using liquid as media. Perhaps the biggest one is the dirtiness, the potential for contamination. If you use a liquid media, that could contaminate the device under test. For example, that device under test is used in a process that doesn't allow for liquid contamination. Then you'll have the challenge of, if you calibrate it with liquid, then you'll have to make sure you thoroughly clean it before putting it back into the system. Or even if it's used with a liquid other than what your calibration system is, you could end up causing contamination either of the device under test and its process, or contamination of your calibration system, and thus contaminating the next device under test that goes down. And contamination in a calibration system can be a very big issue. For example, if you're using a deadweight tester, which is a common type of reference standard used for high pressure calibration, they're designed to work with a specific oil or a specific liquid. If you use a different one that has different properties, that could lead to damage of the piston and cylinder, which can be a very costly mistake. If contamination is a concern, a gas system might be preferable, but you need to take into consideration the equipment that's available and the type of application, and especially for the higher pressures above 3,000 psi. And finally, let's look at pressure stability. Pressure stability, or instability, can be a bigger issue at higher pressures. First off, temperature is more of an influence with liquids than gas. And there's more expansion and contraction of the pressure lines when you're going to those high pressures. So that can make it very challenging to get a stable pressure. If you use a comparison test pump, like what we showed before, you'll get up to those pressures and the pressure will start leaking off. And that leak is not a leak of the fluid, that's temperature effects causing the pressure to decrease. But we can minimize this. So for the lower high pressures, the 3,000 psi type range, gas devices will provide a more stable pressure because they're less impacted by temperature. And then for the higher pressures, where we are using liquids, deadweight testers provide the most stable pressures. Basically what happens is that the sinking piston that's at the heart of the deadweight tester acts as a natural pressure regulator. So the pressure increases, that affects the temperature, which causes the pressure to decrease, but the piston will be sinking, and that decreases the volume in the system, counteracting the temperature effects, and you end up with a stable pressure. Because as long as the piston is floating, pressure equals force over area, there's only one, the piston is floating with a given force and has a given area, there's only one pressure it can be floating at, so you end up with a stable pressure. Hence why deadweight testers have historically been very popular for these type of applications and continue to be even till today. So let's look at the equipment determination. How do you decide what equipment to use for high pressure calibration? There's different things you want to look at here, different aspects of the application. The first is this going to be a benchtop system where you're using it in the field? And that gives you more choices to choose from versus a portable application. And with a portable application, you want something that's smaller, easier to maneuver and take out into the field. But at the same time, if you choose a portable calibrator, but you're going to be using it on the benchtop, then you've made some compromises that perhaps will make it more difficult to operate. You also want to look at, do you want a hydraulic system or a pneumatic system? That's going to depend very much on pressure range, and also your particular application and process of, is contamination a concern? And then you want to look at ease of use. How do you make sure that you can do the most calibrations in the least amount of time so you can meet your calibration needs? And so you want to look at physical effort required to generate pressures and the stability of the pressure. So maybe you can quickly get to a pressure, but it's completely unstable and you have to wait for a period of time for it to stabilize. So those are things that we want to think about when choosing different equipment. And here's a couple of equipment that you could use for high pressure calibration. For high pressure gas at 3,000 psi range, Fluke Calibration offers the 700 HPPK pneumatic pressure pump and calibration kit that goes with it. So what you see here on the right is the full kit with the pump. It looks like a traditional bicycle pump, but it's able to generate 3,000 psi very quickly. The complete system includes the manifold system that you see kind of in the bottom of the picture there. And that manifold system includes quick connections to connect up the reference gauge as well as connect to the device under test. And then it has a screw press or a variable volume that's used to fine tune the pressure and get to exactly the pressure that you need to go to. If you're more concerned about just generating the pressure and not worried about fine tuning the pressure, then it's available with just the pump and without the manifold assembly. Or the other way, if say you're connecting, if you're using this bench top in your shop and not going out in the field, then you can get just the manifold block and use that to fine tune the pressures to connect to, say, a gas bottle, and you can fine tune as the pressure is coming in, you can exhaust it out, and then or when you're at your pressure, you can correct it and make sure you're at exactly the pressure you need it to be. So this makes it ideal for operation in the field. Also, benchtop in the field, it has the carrying case or the strap so you can easily carry it around. And you don't have to set it on top of a bench or anything to generate the pressure. You can just set it up on the ground, pump up the pressure you need quickly and easily so that you can do calibrations up to 3,000 psi in the field with gas. And by using gas, you can have a more stable pressure and you don't have to worry about contaminating the system. So that's especially useful for like a natural gas type system or things along those lines. But if you need to go to higher pressures above 3,000 psi, that's where you may want to switch to a liquid system. So an example of what you could use there, if you're very much interested in something that will provide stable pressures, then you'll want to look at a deadweight tester. An example of deadweight tester available is like the P3100 series. The particular one here is a P3124 that can go to 10,000 psi. It has both a low range and a high range piston cylinder, so that you can do both low pressures and high pressures. So this allows you to cover a very wide pressure range in one instrument, and the floating piston provides a stable, precise, and accurate pressure. Depending upon the accuracy of the pressure measurement that you need, you can either go with the pressures that are marked on each mass to sum those up and get a pressure measurement, or you can do a number of corrections to get a higher accuracy pressure measurement. So it gives you quite a bit of variability and so forth. It should be noted that deadweight testers aren't necessarily the best to take out in the field because you do have to have the set of masses to go with it to generate the higher pressures. So if it's a field type application, then you may look at one of the different pressure pumps that are available on the market that's able to generate the higher pressures with liquid to handle that application, so you don't have to lug masses everywhere that you go. But for a benchtop type application, a deadweight tester provides a great solution. It's common nowadays also, instead of a deadweight tester, you perhaps go with a comparison test pump, perhaps a very similar device, but instead of the piston cylinder with the masses, you just have a reference gauge there. That's a less expensive and perhaps a quicker solution, but you risk the chance of having to worry about pressure stability because you no longer have the sinking piston that's generating stable pressures for you. So with high pressure calibrations, you need to make sure you consider safety, contamination, as well as pressure stability. But by doing so, and by choosing the right equipment, then you can have safe and effective pressure calibrations. So at this time, we'll go ahead and open it up to questions.
Okay, thanks. My contact information is here for anyone that does have questions that aren't answered during this time, but I am going to open it up to the questions that have been submitted. And as a reminder, any questions can be submitted to the right side of your webinar controls, and I'll read through them right now. Okay, first one, will the differential pressure reading of water be the same whether using gauge or absolute differential pressure sensors?
So the differential pressure of water be the same whether you're reading gauge or absolute. Not completely sure I'm following the question. If you're referring to like the example of like the swimming pool where the pressure is greater on the bottom than the top, you can think of it as an absolute mode measurement because at the bottom you don't have barometric pressure to compare it to. But the difference in pressure will be the same whether you're talking about absolute or gauge. If you're referring to like the inches of water pressure measurement, inches of water is normally used for either a gauge or differential mode measurement. Absolute, you'd be an inch of water absolute. You're talking about something that's just slightly above a perfect vacuum. So inches of water is normally not used for that application.
Okay, after instrument calibration, I'm not sure if he's asking a question or making a statement. After instrument calibration, there is need to compute instrument uncertainty. Can you throw more light on how this is to be achieved for pressure sensors?
Okay, well, we can have an entire series of webinars on calculating pressure uncertainty.
Yeah, right.
It depends upon the sensor that you're using, but generally speaking, there's 4 or 5 different components that need to be considered in the uncertainty calculation. The first off is kind of the inherent performance of the pressure sensor. It's linearity, hysteresis, and repeatability. Those describe basically how well does it measure pressure as far as is its output predictable. Those 3 terms are often combined into one term called precision. In addition to that, the other components would be the stability over time. The pressure sensor's output will change with time. And so it will drift with time. There's 2 ways that it normally drifts. The zero stability, that is when it's, say it's a gauge mode sensor, it's open to atmosphere. With time, it will no longer read 0, but that's an easily correctable one. But with absolute, it's not as easily correctable, so you may have to include that in the uncertainty. The other thing is the span drift. And that drifts over time, but that's corrected when we recalibrate it. So for most devices, the specifications will include a precision specification, and they'll include a drift specification. That is, over a given period of time, usually 1 year, maybe 6 months, but usually 1 year, say, okay, it's allowed to drift this much over that 1 year. You would combine those to get kind of the overall specification of the device, but then you'd also look at for the uncertainty, you also need to consider the uncertainty of the reference standard that you're using to calibrate it. And then for your overall uncertainty measurement, you'd also include like head height. How well did you know the difference in height between the place where you're making the measurement and the place where you care about what the pressure is? So the difference between the reference and the device under test. Those are kind of the main components. For certain applications, you may also include like pressure stability. So you would look at perhaps take a number of measurements over a quick period of time, average those together, and then look at the standard deviation, include that in your uncertainty as well. There's a number of documents available on flukecal.com that go into this detail, some to a pretty high level, but you can look at the examples there to see pressure uncertainty calculations for those. We also provide like a week-long class where we'll dive into the subject as well.
Okay. We currently use oil for everything over 300 psi. Should we use gas instead?
Maybe. If you're having an issue with contamination, so say you've got some 1,000 psi gauges and you're contaminating with oil, and your customers are saying, hey, this is a problem, or you're spending a lot of time cleaning them after using them or after calibrating them, then you may want to consider going to gas. Using oil for things above 300 psi has been pretty common in our industry, especially for portable applications. But you may find gas, and like using the 700 HPPK is a preferable solution. That said, if it ain't broke, don't fix it. If using the oil has not caused a problem and it's not causing an issue with your customers, with the users of the stuff that you calibrate, then by all means stick with it. But you may find that gas is a cleaner and easier solution now that equipment is available for generating those pressures.
Okay. Can you go over again why, as long as the table of a dead weight tester is floating, it is getting an accurate reading? Okay.
So a dead weight tester works on the principle of pressure equals force divided by area. And there's a number of corrections to that. There's a really long equation that calculates out the pressure for a dead weight tester. But the general concept is that the force in the pressure equals force over area. The force is the masses being accelerated by gravity. And the area is the effective area of the piston and cylinder. If it's floating, then the pressure underneath the piston is equal to the force being applied above it, or being applied down on it by the masses, divided by the effective area of the piston cylinder. If the piston's floating, then those two things are constant, the force and the area of the piston cylinder, and so you generally have a stable pressure. Now there are corrections to that, like the temperature of the piston cylinder will change the effective area, or the piston will expand and contract with pressure, so the area will be affected by the pressure. But when you're at the pressure, those kind of stabilize out, and so as long as the piston is floating, then everything is good. With the caveat that if you have any other forces in play, then that creates instability. So if there's friction between the piston and cylinder, then you would no longer have a stable pressure. So that's where we rotate the masses to center the piston and to show there's no no vertical friction between the piston and cylinder. So if it's floating, masses are rotating, then you'll end up with a stable pressure, and it won't be changing on you or dropping like it would with a normal comparison test pump. How it does that is that the piston does naturally sink, and that changes the volume in the system. So if there's temperature changes in the system, it's being counteracted by the sinking of the piston. What that also means is if there's dramatic changes in temperature, you'll have dramatic sinking of the piston, and it may not float long enough to take a measurement. But while it's floating, everything's stable, and you've got a stable pressure.
Okay. I think that's it for questions at this time. So that concludes our time for today. Thank you, Tim. If you have further questions or would like to find out about Transcat's product and service offerings, you can contact us at the 800 number on the last slide, 800-800-5001, at our website, transcat.com, or you can contact me directly. My email address is there. Thank you all for joining us today, and we hope you got something out of today's presentation. We will follow up in a few days with the recorded webinar. Thanks again.